All right. So when we left off last week, we ended with talking about standard normal distribution and what some basic characteristics of that are. We're going to move on to talking about finding the area under a normal distribution now. Excuse me. So the first thing you might ask is, why do we care about what the area is under this normal distribution curve? It's really quite simple. The area under the curve gives you the probability that a value in your data set falls in that region, um, which is really very useful in what we need from statistics most of the time. And most of what we're interested in as statisticians or scientists, it comes pretty close to a normal distribution. So really, it works well to use the normal distribution for this. Get my laser pointer. There we go. Um, so we've got some, just notation. The probability that the value we're interested in falls below some certain score, or the value that it falls above some certain score, that's written in those ways. Um, we don't talk about x being a specific value. We talk about it being within a range, because this is a continuous distribution. There are really an infinite number of values it could be. As you know, 0.999 repeating is infinitely close to 0.9998, etc. So there's ways we can do this. We can use calculus and integrate the curve if we know the formula for it. That's beyond the scope of this course, well beyond the scope of this course. Plus, as we mentioned briefly last week, every curve is technically unique, which is why we use the standard normal curve that we talked about. We convert it to a standard curve, take the difference between the value and the mean and divide by this standard deviation to get your standard curve values. What this gives us, though, is a curve where um, everything is set. We don't need to redo all the calculations over and over again. We can record them, and it can be programmed into a calculator or software a little more easily, or put in table form, as you'll see in Appendix A and B in your book. These are what they call cumulative normal distribution tables. So let me go ahead. The value here is the probability that the value is less than 0, less than 0.1. These are written in such a way, so this would be 0.0, 0.1, 0, sorry, 0.01, 0.02. So your first digit is here. So this would be 1, 1.0. So 0.1, 0.11, 0.12, 0.13. So you've got the first decimal point in this, and gives you the row. This decimal point after that gives you what column you're after. Which I just explained. All right, so let's see how this works. We want to find the area under a standard normal curve, what the area is to the left of 1.37. So go ahead and pull up. Actually, let's pause while I'm pulling this up. No, don't need to pause for this. I've got it right here. There we go. There we go. We want 1.37. So table A gives z values from negative 3.4 to negative 0.0. So this would be negative 0.01, negative 0.09, etc. So the standard normal distribution, we've got the negative side of the curve and the positive side of the curve here. You'll note that at a value of 0.0, that's 50% of the curve, right? So we're after 1.37, so there's 1.3. And we go over here to, this row. One of the things you may notice about these tables is they typically alternate between a slightly shaded and unshaded to make it easy for you to not lose track of where you are. So there's 1.37, see there's 0.07 there. So this is 0.914. So if this is 1.37, the z-value we're after, the area under that curve is 0.9147. Okay, let's minimize that again. Okay, so did I misread that? They've got 0.9147. I must have misread it. I'm fairly certain I said 0.9137. So that is what I just showed you. And again, that's, oops. There we go. Get my laser pointer back. There we go. The area under the shaded part is 0.9147. So our 1.37 that we're looking at. I am not going to go over the how to do this in the TI-83 or 84 plus calculator. I will post these slides so you can do that on your own if you have that. What I am going to do, because it's not covered here, and frankly I do find Excel more useful, is talk briefly about what you would use in Excel, very briefly. And I'm mostly covering this because it's not, there is a z-test in there. It's not what we're after here. The function we need is the norm.s.dist function, and that gives us the probability. We give it the z-value, tell it we want cumulative. Let's look at the examples. So we tell it true if we want a cumulative one. So it gives us the probability associated of everything to the left of that z-value. I am not familiar offhand with the probability mass function, so that's something slightly different. For what we're talking about here, we'd want to set that at true, so you'd give it norm.s.dist, the z-value you're interested in, and true, and it will do the same thing as we just looked up in the table, or what I just skipped showing you on the calculator. Okay, let's go back here, make sure I've got that selected. Okay. All right. So that tells us, as you can see here in these graphs, that tells us what the probability is of something being to the left of the z-value we're interested in. What if we're interested in something to the right? All right, so there are a couple of ways we can do this. First is by remembering that the total area under the curve is going to be 1. So if we figure out what the probability is that on the left-hand side, subtract that from 1, we've got the probability that's going to be on the right-hand side. The other way to do it is to remember that this curve is symmetrical. If we just find the negative of the probability, if instead of looking up z in the table, we look up negative z, that's going to be our probability. So if you look at the figures here, if we're interested in what's to the right of z, what that probability is, that is going to be the same area as what is to the left of negative z. So we can look up negative z in the table, and that will give us the answer for what's to the right of positive z. Again, to reiterate, the area under this whole thing is going to be 1. So if we look up the value, the probability to the left of z, which is what the table is going to give us, and subtracts that from 1, that's going to give us what's left over, which is this part here. Either way works just fine. Okay, so we did our previous example with 1.37. We can use that first method. What is the value to the right? If we subtract this 0.9147 that we previously found from 1, we get 0.0853, right? So there's our 0.9147 we found before. 1 minus 0.9147 should give us our answer. The other thing we can do is look up negative 1.37 on the table, right? Because the curve is symmetric, so that negative 1.37 should have the same area out here as 1.37 does out here. If we took this and folded it in half, those two would line up, so that those areas have to be the same. And sure enough, at 1.37 we get negative 0.853. Okay. For a minute. Okay. All right, so let's do another example. Let's find the area to the right of negative 0.9. All right. So if you've got your textbook handy, go ahead and pause and do that, and unpause and continue when you're ready. Okay, so a couple of ways to do that. We can look up negative 0.9 in table A and see that we've got 0.1841 to the left of that. If we subtract that from 1, we get the answer we're looking for, the area to the right of negative 0.9, which is 0.8159. The other thing we can do is look up positive 0.9, and we'll end up with the same number. Right? Okay, so if we wanted to do this with TI, there's the instructions there. I will leave that to you if you want to do this. You can find the area between two z values. There's a way to do that directly with TI. What you would do is find the area to the right of one value and the area to the left of the other value. Actually, you'd want to find the area to the left of both values. That's the easiest, and subtract off the smaller of those, and that's going to be the area in between. Let's see. So, right. So in this example, if we want to find the area between 1.5 and 2.75, we find the area to the left of 1.5 and the area to the left of 2.75, and we subtract the area that was to the left of 1.5 from the area that was to the left of 2.75, and that'll give us that area that's in between. All right, let's skip the TI. We can also find the area for tails. We'd be finding the area to the right on one side and the area to the left on the other side and adding them up. Or you can find the area in between them and subtract that from 1. Right. If you've got a symmetrical tail, you can find one of the areas and multiply it by 2. A lot of this is a little bit easier if you think about it in if you go ahead and just think about it graphically, and remember things are symmetrical and the sum is going to be 1. Okay. These last few slides are intended as review. If you want to find the area to the left of something, less than, you look up that value. If you want to find the area to the right hand, so the probability that something's greater than what you're looking for, or than the value you've set as your limit, look up the negative of that value. If you want the probability that your answer is in between two values, look up the two values and subtract the area to the left of the smaller of them. If you want to find tails, so probability of it being less than one value or greater than another value, look up the two values. In this case, look up one value and the negative of the positive value of the one farthest to the right, and add those areas. And there's the handy calculator functions for all of those. All right. So again, this is vocabulary here. So what is the probability that z, this whatever it is we're looking for, is less than or equal to negative 2.76? That is going to be the area under the standard curve to the left of negative 2.76. So that little bit right there. And note that the equal sign doesn't actually change the probability here. That z is less than negative 2.76 is the same probability as z is less than or equal to negative 2.76. We're not going to actually wade through all of these examples here in the lecture. Feel free to go and do that on your own, using any of the methods. I encourage you to use multiple methods to get a feel for them, and I would throw in Excel as a possibility here as well. So I'm going to skip through all of these. I believe that was it. Yeah, that's it.